Good morning, Professor T. N. Oza here. I am going to present a new video based on nuclear magnetic resonance technique. In this video, we shall be discussing fundamental principles. Application part will be discussed in a later video. For clarity of the subject, the whole topic has been divided into so many small parts listed over here. So let us begin with the introduction part. Introduction to nuclear magnetic resonance spectroscopic technique. Some atomic nuclei possess intrinsic spin symbol I characterized by spin angular momentum vector. By virtue of the spinning electrical charge, such nuclei behave as tiny bar magnets. When exposed to an external magnetic field B, the degenerate spin states are split into 2I plus 1 quantized energy states. For spin half nuclei, two energy states are created. This process is called Zeeman splitting under the influence of external magnetic field. When energy equal to the separation between the upper and lower energy states, which is proportional to the magnetic field B, is supplied, spin flip takes place. Nuclei located in different chemical environment in the molecule absorb at different frequencies. And this feature constitutes the most important aspect of NMR spectroscopy. I repeat this point. Nuclei located in different chemical environments absorb at different frequencies. This is the most important feature. The measurement of these frequencies, or alternatively the measurement of the corresponding magnetic field values, constitutes the realm of NMR spectrometry, which is the most powerful and versatile structural technique. Nearly 50 nuclei are found to be NMR active, out of which some are very important, very useful. Examples are proton or hydrogen 1, carbon 13, fluorine 19, and phosphorus 31. These nuclei have been extensively studied. Many other nuclei have also been studied. As I told you, nearly 50 nuclei are studied by NMR. But these are most extensively studied, most useful. They provide very dependable data. The discovery of NMR. The phenomenon called nuclear magnetic resonance absorption was independently discovered by two groups of American physicists. One, E.M. Poschel et al. At Harvard University, and another, F. Bloch et al. At Stanford University. It may be noted that the discovery of NMR followed the discovery of ESR, electron spin resonance, by the Soviet physicist E. Zhavisky in 1944-45. NMR came in 1945-46. A matter of great satisfaction for us is, in one of the team led by Purcell, one Indian scientist was also included, S.S. Dharmati of the Institute of Science, Bombay. The first NMR spectrum which was recorded was of ethanol. It contains three kinds of hydrogens, CH3, one type, CH2, another type, OH, third type. So it provided three signals, and this gave the encouragement for further study. Purcell and Bloch were awarded 1952 Physics Nobel Prize. The NMR experiment. The old method of recording the NMR spectrum of a sample is called continuous wave method, CW method. In this method, 20 to 50 milligram sample is dissolved in a deuterated solvent, preferably deuterated chloroform. Then 2 to 3 drops of an internal reference compound, mostly tetramethylsilane, is added to the solution. The solution is contained in NMR tube, which is a very thin glass tube, narrow diameter, about 20 centimeter length. This sample tube is placed between the poles of a very powerful Harsu electromagnet with supplied DC current. The sample tube is rotated through a spinner. Why it is rotated? So that all molecules experience an average magnetic field. Then a fixed frequency is supplied by a crystal controlled oscillator, radio frequency oscillator. The radio frequency receiver measures the amount of absorption. NMR scan is taken by sweeping through the finally varied magnetic field. The spectrum is displayed by using an oscilloscope. Why do we use TMS? TMS is preferred for several reasons. Firstly, it is a low boiling liquid, 27 degrees Celsius is boiling point. So after the experiment is over, it goes off automatically so that the sample is recovered. Secondly, it is non-toxic, not a health hazard. Thirdly, it is less inflammable. Fourthly, it is miscible with most of the organic solvents. And its very important feature, its protons are more shielded than other protons in organic molecules. Therefore, its signal appears at the extreme right end, that is the highest magnetic field end. So its signal can be easily identified. And moreover, its signal is very sharp because there are 12 identical hydrogens, chemically equivalent hydrogens. The outline of NMR experiment is shown in this diagram, speculative diagram. You see, a sample tube is placed between the poles of a magnet. The magnet is supplied with sweep coil so as the field can be varied, finally varied. A spinner rotates the sample tube. RF oscillator provides the fixed radio frequency. RF receiver measures the amount of absorption and the data is transmitted to recorder computer. And how do we report the data? TMS signal is at the extreme right because its hydrogens are most shielded. Later we will explain it in more detail. The left side is called downfield side because magnetic field increases from left to right. Its data is reported in delta scale, which is a unitless scale, universal scale. And for TMS signal, arbitrarily delta value is set at 0. Arbitrarily, not truly. Scope of NMR spectrometry. In chemistry, any branch of science which uses chemicals, NMR is there. And the technique is so important, so indispensable that if some problem has not been studied by NMR, we can say there is something yet to be studied. This much important. I think at present the most important technique is NMR. The technique is mainly used for structural determination of molecules, stereochemistry, conformation analysis, entropy study, polymeric species, surface phenomenon, fast reaction kinetics, viscosity, dielectric constant, crystal anisotropy, and many other problems. MRI, which is very common in medical field these days, is actually based on NMR only. It is an application of NMR. So let us go to the basic principles. First thing we will discuss, nuclear spin vector I. You know, proton and neutron possess intrinsic spin of quantum number half each. The resultant of the spins of protons and neutrons in the nucleus gives rise to the nuclear spin quantum number I. For example, hydrogen has only proton, so naturally its spin will be half. Deuterium, the heavy isotope of hydrogen, has one neutron and one proton. So there are two possibilities. If both spins are empty, then total spin will be 0. If both spins are parallel, total spin will be 1. Practically, it has been found that deuterium has spin 1. And both some generalizations have been given by Professor J. Popele because spin quantum number cannot be calculated. So, on the basis of his studies, experimental study, Professor J. Popele, a Nobel laureate physicist, gave certain generalizations. He told if a nucleus has even number of proton and even number of neutrons, then its spin will be 0 because all spins will be paired up. Secondly, when the proton number and neutron number both are odd numbers, so that atomic mass number is even number, such nuclei have integral spin. Deuterium, for example, has spin 1. Nitrogen 14 has spin 1. Boron 10 has spin 3. Next, if the sum of proton and neutron is odd number, then spin is either half or multiple of half, but half integral only, not whole integral. The nuclei which have spin half are hydrogen, carbon 13, nitrogen 15, fluorine 19, silicon 29, phosphorus 31, tin 119, platinum 195. Higher nuclear spins are also known. For example, 3 by 2 for boron 11, 5 by 2 for oxygen 17. Up to spin values up to 9.9 by 2 are known for transition metal ions. But those nuclei which have spin half are spherical in shape and give very good NMR spectra, well resolved spectra. Those nuclei which have spin more than half, either positive or negative, they are called quadrupolar because their nuclear charge is so distributed that four poles are created. Their NMR spectra are broad, not well designed, well resolved. Presence of quadrupolar nucleus also destroys the spectra of other nuclei by causing broadening effect. However, quadrupolar nuclei are studied by a technique known as nuclear quadrupole resonance. Now we will proceed taking the simplest example of hydrogen atom. The theoretical basis which we will discuss now on hydrogen atom is applicable to all other nuclei. So let us begin with the hydrogen atom, that is proton. Its spin quantum number is half. It means the spin vector is h upon 2 pi multiplied by under root of I plus 1. It gives out under root 3 by 2 h cross equal to 0.866 h cross. Putting the value of h cross, it becomes 0.91363 into 10 to the power minus 34 joule second. The same is the case of electron, where spin quantum number is half, and the spin vector is 0.866 h cross. I have included this for comparison purpose. Now, resolution of spin vector. As a rule, any vector can be resolved into how many components? The number of components possible is 2 multiplied by quantum number plus 1. So for proton, spin quantum number is half. Applying this formula, we can say that only two orientations are possible. One designated by minus half, other designated by plus half. And the respective components of spin vector are symbolized by Iz, having values mi h cross, where mi equal to plus minus half. If some nucleus has a spin more than half, for example 3 by 2, then the possible components are plus 3 by 2, plus half, minus 3 by 2, so on and so forth. Put simply, for integral spin nuclei, suppose the spin is integral, then the components are I minus 1, I minus 2, through 0, minus I minus 2, minus I minus 1, up to minus I. Total 2I plus 1 values. If the nucleus is half integral type spin, then the values don't include zero value. Nuclear magnetic moment. As I told earlier, those nuclei which possess the spin, they possess a spin vector. And nuclei are positively charged. So spinning of this positive charge creates magnetic moment. And magnetic moment is proportional to the spin vector. By putting a constant, you can write mu n, that is magnetic moment of the nucleus, equal to gamma I. This constant gamma is a tensor. It is called magneto-gyric ratio. In older literature, the term was called gyri magnetic ratio, but now it was realized that that was the wrong description. So it should be called magneto-gyric ratio because its value is mu n upon I. Its value for proton is 2.675 into 10 to the power 8 per second per Tesla. The quantum mechanical equivalent of gyromagnetic ratio, gamma, is Gn mu n upon h cross, or we can say gamma h cross equal to Gn mu n, where mu n is Gn mu n under root I plus 1. You see, mu with capital N is a unit, natural unit. The G factor for proton is 5.585. The nuclear magneton, symbol mu subscripted by capital N, is the natural unit for expressing the magnetic moment of particles such as nuclei. Its value is mu n equal to EH upon 4 pi mp. mp means mass of proton, E means charge of proton, pi is a constant, you know. The value comes out to be 5.051 multiplied by 10 to the power minus 27 joule per Tesla. It means the magnetic moment of proton will be equal to 5.585 multiplied by 5.051 into 10 to the power minus 27 joule per Tesla into 0.866. It comes out to be 2.44 into 10 to the power minus 26 joule per Tesla. Very small value. Here it may be noted that electron magnetic moments, which are 660 times larger than proton magnetic moment, are expressed in Bohr magneton unit. The Bohr magneton unit mu b, sometimes also symbolized by the symbol beta, is given by EH upon 4 pi MeV. MeV is mass of electron, which is 9.108 into 10 to the power minus 31 kilogram. E charge, which is 1.602 into 20 to the power minus 19 coulomb. The difference in the values of mu b and mu n are two regions, difference in their masses, which are in the ratio MB versus MBP, 1 is to 1837, and difference in their G values, 2 for electron, 5.585 for proton. In the absence of an external magnetic field, all possible directions of vector I are equally populated, resulting into no net magnetization. But the moment an external magnetic field greater than zero is applied along the z direction by convention. Only two orientations of the spin vector are allowed. One along the field axis, that is parallel to the field axis, and another in the anti-parallel position. Here, the parallel situation is attractive, that is of low energy. Anti-parallel situation is repulsive, of higher energy. The Boltzmann equation for population distribution. As I told earlier, when magnetic field is applied, the degeneracy of the spin levels is removed and two clear-cut energy levels are created. The separation between these two energy states is very, very small. The result is both spin levels are almost nearly equally populated. An example you will be surprised to note, if there are 10 to the power 6 nuclei in the upper spin state, then the lower spin states has 10 to the power 6 plus 7, plus 7. Only difference of 7 nuclei. But the NMR technique is so powerful, so sensitive, that it can pick up the small difference and the spectrum can be recorded. The interaction between the external magnetic field B0 and the nuclear spin vector I, that is energy of interaction, EMI. This is given by equation negative mu1 times B0 cos theta. Considering the z component, we can write plus minus half equal to minus mu z bz. Here mu z, as I told earlier, is equal to Gn mu n upon h dot whole multiplied by Iz. This can also be written as gamma Iz. So for the two spin states, energy equations are written as equation 6. The separation between these two states, delta E, is Gn mu n Bz. Alternatively, it can be written as gamma Bz h upon 2 pi, equation number 7. When the energy of the supplied radiation, delta E, agrees with this, the condition is called Bohr-Einstein resonance condition. In NMR frequency scale, the delta E has to be divided by h, and we get mu NMR is gamma upon 2 pi multiplied by Bz. Equation number 8. If we calculate the value for 1 Tesla, it comes out to be 42.577 megahertz per Tesla. NMR absorption. In principle, NMR spectra can be obtained by either sweeping through the magnetic field while keeping the radio frequency constant, for example 100 megahertz for the magnetic field of 2.35 Tesla, or vice versa. Routinely, the spectra are run by varying the field because technically it is easier. When energy in the form of radio waves, which are nowadays used between 100 to 900 megahertz, depending on the VZ value, it's applied to the sample, a spin flip from plus half to minus half takes place. This phenomenon is called nuclear magnetic resonance absorption. For 1 Tesla field, NMR frequency will be about 42.58 megahertz. Similarly, for field of 1.4092 Tesla, the frequency will be in the vicinity of 60 megahertz. These days, helium-cooled solenoid-based magnets of as high as 21 Tesla field are available, and they correspond to an NMR frequency of about 900 megahertz. For NMR study, higher fields are preferred. This improves the population difference between upper and lower energy states. Here, the line diagram explains the things very clearly. You see, when no magnetic field is applied, the spin states are degenerate. When field is applied, the minus half state is raised into energy, plus half state is lowered into energy, and difference between the two states is given by delta E, Gn, mu and Bz. As the field increases, the separation increases. And this is Zeeman splitting, shown in this figure. Zeeman splitting of spin states under the influence of external magnetic field. Chemical shift, number of signals, areas, and splitting of peaks. The net magnetic moment of spin paired electrons, each being a teeny bar magnet, is itself zero. Actually, the electronic environment around the proton in the molecule is the most important feature. The field which is applied does not reach to the nucleus as such. It gets modified. Why modified? Because the surrounding electrons are the surrounding electrons create a dimagnetic field which opposes the applied field. In some cases, the induced field dimagnetism has two components, one along the field direction and one opposite to it. So very complicated influences take place. In nutshell, we can say the electronic environment around the particular hydrogen in the molecule makes all the difference. This creates what is known as chemical shift. The equation very clearly shows this. The field reaching the nucleus, that is B effective, is field applied B0 minus sigma multiplied by B0. But this sigma is called shielding constant, the dimensionless parameter, somehow related to diamagnetic susceptibility of the molecule. And this makes NMR the most important tool. Correctly speaking, chemical shift is defined as minus sigma I B0, where sigma I refers to the shielding constant of the IS nucleus and B0 refers to the applied field. This sigma, which is shielding constant, has a very small magnitude, but even this much causes all the importance. The things are more clearly shown in this diagram. Frequency increases from right to left, magnetic field from left to right, PMS signal is at the extreme right, and the separation between signal of compound H, that means hydrogen, and TMS is called chemical shift. Here one very important thing, actually chemical shifts are field dependent. So for each and every machine, the value will be different, no use at all. Therefore, by mathematical manipulation, it has been converted to international scale, which is field independent. That scale is called delta scale. The formula is delta is calculated by observed shift in Hertz divided by spectrometer operating frequency in Hertz whole multiplied by 10 to the power 6. And then ppm is added. ppm means 10 to the power minus 6. So 10 to the power 6 ppm means 1. Why do we add this 10 to the power 6 multiplied factor? Because the values obtained for delta are so small that it is difficult to remember them. By multiplying by 10 to the power 6, they become memorizable. That is why this delta scale is used. In older literature, tau scale was used, but this has been done away with. Anyway, older books data can be converted to delta scale by using the formula delta plus tau equal to 10. This simple formula helps us convert tau scale values into delta scale value. A compound shows as many PMR signals as the chemically different types of hydrogens in it. Multiplicities reveal the number of H or F or P on adjacent carbons. Sometimes we use the abbreviations singlet S, doublet D, triplet T, quartet Q, quintet QN, multiplet M, broad peak BR, etc. etc. As I told earlier, the chemical shift data are reported in delta scale, which is dimensionless and universal scale. The spectrum recorded on any machine will have the same delta value. Here I have included two examples. In one case, I have considered para di-tertiary butyl benzene. See, there are two kinds of hydrogens. The methyl hydrogens, which are 18 in number, chemically equivalent, and aromatic hydrogens, which are 4 in number, also chemically equivalent. So we observe two signals. And not only this, the signal heights are in the ratio of the number of protons. Here the ratio is 9:2. In another example, and this signal, alkyl protons absorb between 2 to 1.5 ppm, while aromatic protons absorb between 8 to 7 ppm. Another example, CH2CHF, fluoroethylene. It seems that there are only two types of hydrogens, but not. There are three types of hydrogens. Of the CH2 part, one hydrogen is cis to fluorine, while another hydrogen is trans to fluorine. So this molecule, this simple molecule, CH2 double bond CHF, has chemically three non-equivalent hydrogens. There are three signals. Each signal is split by the nearby hydrogens into DD pattern, and also split by fluorine because the fluorine nucleus is also a magnet. So in this simple molecule, the spectrum contains three bunches of 8 signals each, 8 lines each. A numerical problem. Let us suppose that the operating frequency of a multinuclear NMR spectrometer is 500 MHz. Then where to look for the resonance signals for proton, carbon 13, fluorine 19, phosphorus 31 separately? The hint is given. Magnetic field can be calculated using the formula magnetic field Bz equal to h nu upon Gn mu n. So this Gn value is different for all nuclei. It is 5.585 for proton, 1.404 for carbon 13, 5.255 for fluorine 19, and 2.261 for phosphorus 31. If we put the values, the frequencies for different nuclei, proton, fluorine, carbon, and phosphorus are found in the ratio 100, 94.1, 25.1, 40.1. But not at one time. Only one type of nucleus can be studied. For other type of nuclei, the instrument has to be readjusted according to the requirement. Here I have given a hand-drawn diagram. The first part shows the spinning nucleus. The second part shows the spin vector, which is like a cone. Two components, negative z-axis and plus z-axis, are shown. The component Iz upon I is equal to cos theta plus Iz equal to I cos theta. The theta value is around 54 degrees, 44 minutes. In the next diagram, I have shown a splitting of energy states when the field is applied. When no field was present, the spin states were degenerate, and field was applied, G-mono splitting takes place. All these things have been discussed in earlier slides also. So I hope this will be a very helpful video because I have included the fundamental principles. The application part will be given in some later video. Thank you very much.